In this lecture, we will learn how to explain the concept of variability, find and interpret the range of a distribution, and find and interpret the interquartile range of a distribution. Variability literally means the ability to vary, or to have more than one value. As a property, variability increases as the number of possible values increases. Table 4.1 illustrates how different data sets can seem similar if one only looks at the mean value. However, when one looks at the individual scores, you can learn a lot more about the data and have a better understanding of how the sets are or are not similar. We won't be directly discussing bias in this lecture, but I like this bullseye graphic because it shows how two sets of data can both result in an accurate response. Accurate being represented by hitting the bullseye within the average of all the dots, while one set of data clearly has less variation than the other. Let's contrast two data sets to determine which set is more variable. We should be able to simply eyeball the two data sets to get an idea as to their relative variability. Dataset 1 ranges from -5 to +3, while dataset 2 ranges from -4 to +2. Thus, just from eyeballing it, I can see there are less possible values in dataset number 2, making it less variable than dataset 1. Instinctively, we looked at a characteristic of the two datasets on the previous slide called the range. The range of a quantitative variable is the highest score minus the lowest score, where x is again the symbol for score, and the subscripts h and l are used to designate high and low. Let's calculate the range for both sets of data. The x sub h score for dataset number 1 is 3. And the x sub l score is -5. Thus, the range is 3 minus a -5, which if you'll remember from a long time ago, anytime you have two minuses, it becomes a plus, which equals 3 plus 5, or 8. Think of the numbers spread out on a number line. The range will represent the distance between the minimum and maximum values. For dataset number 2, x sub l is -4, and x sub h is 2. 2 minus a -4 is the same thing as 2 plus 4, or 6. Therefore, the range for dataset number 1 is 8, and the range for dataset number 2 is 6. Finally, let's introduce the interquartile range, often abbreviated IQR. The IQR tells the range that represents the middle 50% of all scores. That is, the range of scores from the 25th percentile to the 75th percentile. The percentile is simply a point in a data set below which a specified percentage of the data lie. Graphically, imagine spreading your data out in order, similar to calculating the median. Then, determine how many scores are in each quartile by multiplying the n by 0.25, or 1/4. For this data set, n equals 40, so 0.25 times 40 is 10. Mark off the 25th percentiles at each 10th score. Thus, the lower 25% of scores lie to the left of score 24. Likewise, the top 25% of the values lie to the right of the 30th score. So the 25th percentile is at score 24, and the 75th percentile is at score 28, making the IQR equal to 28 minus 24, or 4. The IQR can be interpreted as the middle 50% of all scores lying between 24 and 28. Let's practice finding the range and interquartile range for another set of scores. In this frequency distribution, the scores have a minimum of 2 and a maximum of 7. Thus, the range is x sub h minus x sub l equals 7 minus 2, which equals 5. To find the IQR, we need to figure out how many total scores we have. To do this, add up the frequency counts. 2 plus 3 plus 5 plus 3 plus 3 plus 3 equals 19. So the n for this distribution is 19. Apparently my little Mew is really vocal tonight. Sorry about that. So 0.25 times n, or 0.25 times 19, gives me 4.75. Just looking at the distribution, the 4.75th score from the bottom of the distribution would be somewhere in the range of value 3. The 4.75th score from the top would lie in the range of value 6. Thus, the interquartile range is 6 minus 3, or simply 3.